two of his students, as well as my student, Untitled Chapter. And, whoops. There we go. Good. All right, so I think over the last almost 15 years or so, there have been a variety of interesting threads in the development of our understanding of scattering amplitudes that for a long time have seemed like they might have sort of something to do with each other, and parts of them seem connected, but not nearly concretely enough, at least certainly not combining them all together. So there's the original idea of the twistor string theory, the amplituhedron, the scattering equations. Of course, somehow these are related to perturbative string amplitudes. More recently, there's some explorations that started late last year, recognizing more algebraically amplitudes as being sort of unique objects that are on-shell gauge invariant. And what I want to tell you about is a picture that's, I think, in a meaningful way unifying all these threads into sort of one object, or at least one sort of paradigm for what's going on. That's what I want to tell you about. And that's associated with these words, that you should think of as amplitudes not as functions, but as certain canonical differential forms that are associated with some positive geometries. And that specifically the things that are somehow related to string theory in one way or the other are also to be thought of as examples where the worldsheet is a positive geometry and have a very, very simple kind of mapping between two kinds of positive geometry. So that's the amplitudes part of the title. Now, when I originally sent my title in, I was under the mistaken impression these talks were 45 minutes long. So there's a whole second part about correlation functions. Now, this is something which I ran into a couple of years ago. I gave some talks about it sporadically last year, here and there, but only recently, together with Paolo Benincasa and Alex Postnikov, have we really understood what these objects are about. And this is a picture that starts doing exactly the same kinds of things for the wave function of a simple scalar field theory in flat space, the analog in de Sitter space, or for ADS boundary correlators. And that's associated with another kind of positive geometry called the cosmological polytope, which we call the cosmological polytope. I'm not going to have time to talk about that at all, but part of the problem a couple of years ago was that it didn't fit in the same logic as we understood about amplitudes, but now the words and the sort of moral story is very, very similar. So that's just an advertisement to look out for that paper when it comes out. All right, so let's just jump right into it. First, let me tell you a little bit about what positive geometries and canonical forms are. I'm going to summarize in 2 slides a 100-page paper that I wrote back in March. So positive geometry is loosely some kind of closed region in some space. And what's important about it is it has boundaries of all possible codimension. Okay, so it has an interior codimension 1, codimension 2, boundaries of all possible codimension. It's a real geometry. But another crucial thing associated with a positive geometry is a certain complex differential form, which has the property of being a unique form, which has logarithmic singularities on all the boundaries, and only on all the boundaries of P. Logarithmic singularities means locally in the neighborhood of any singular locus, it can look like a bunch of wedges of dx over x variables. Now, one generic fact about positive forms, what you really want to know, given a positive geometry, is what's the associated form. In even all our investigations so far, that's what's been directly related to the physics. And so there are sort of 2 methods. There are many more that we talked about in the paper. There's 2 broad methods that are useful. One of them is triangulation, that if you tile a positive geometry by a bunch of smaller pieces, then the form for the big geometry is the sum of the forms for the little ones. That sounds like an obvious statement, but it's not, it does not have a trivial proof. Another one, which is less familiar to us from everyday life or other parts of physics, is the picture of a push forward. That let's say you want the form on this positive geometry. Well, suppose you knew the form on another positive geometry. Maybe it was simpler, or you happen to know it for some reason. All you have to do is find in the real, all you have to do is find the diffeomorphism that maps the interior of this positive geometry 1-to-1 to the interior, including the boundaries of that positive geometry. And then the push forward of the form that you know on one positive geometry gives you the form on the other. Now, typically, these are complicated polynomial equations, and so the preimage of a point back here can be many points here, and of course you have to sum over all of them in order for the form here to push forward to the form there. Now, let's say you wanted, just as a consistency check, someone handed you a conjectured push forward and you're too lazy, it's hard to check whether it really mapped the space or another. A quick check that something magical is going on is that you have to find that if you ask for what all the preimages are of a point inside here, if and only if the point is in P2, there's a single real solution inside P1. The rest of the solutions might be real, they might be complex, but they're not inside P1. Okay, so it's that single real solution is the hallmark in the backwards direction of having a push forward. All right, now let me tell you just abstractly, and then I'll illustrate with many examples, what the general picture is that we're going to see over and over again. The general picture is the following. So we have amplitudes. They're labeled by something. They're labeled by some kinematic data. There might be spinor helicity variables. There might be Mandelstams. We'll see all of these examples as we go. But that's the space. Okay? That's the data you're given. Now, the large question that my collaborators and I have been working on for many, many years, or the class of questions, is what kind of structure, what kind of objects you have to endow this kinematic space with, or relatives of the kinematic space. What question do you have to ask in this space whose answer is the scattering amplitude, right? There's no interior of the space-time anymore. You're just given the actual kinematics, and you want to put some structure on that space that spits out the scattering amplitude. And here's going to be the general structure that we're going to see again and again. The big kinematical space is some big space. It's some capital D dimensional. We'll see that scattering amplitudes are associated with, in general, not top-dimensional, lower-dimensional forms on this big kinematical space. So I'll tell you how that works. Okay, and this form is fixed thusly. Okay, so in this big kinematical space, first there's going to be a space-filling, top-dimensional positive region. I'll call that P. Okay, now, but this is a lower-dimensional form in general. It's a D form. So I need to say something about something interesting that form does. So I have to find some canonical D-dimensional space to pull it back to. Right? So I'm going to find a family of subspaces that are D-dimensional. But the interesting thing is that these subspaces are going to intersect this positive region in some shape. The shape they're intersected in is going to be a positive geometry. And this canonical form, omega d, is going to be uniquely determined by the requirement that it's the canonical form on that positive geometry. Okay, so that's the basic logic. And let me illustrate how this works. Now, the next 5 minutes, 7 minutes are going to go very fast. If you know nothing about the subject, don't worry. I want to just talk about the first place where these ideas arose, but it'll be quite abstract here if you haven't seen any of these things before. Later, we're going to see it in a much simpler setting, which will also have the connection to the Worldsheet and all the rest of it. So, but let's begin by talking about how these things first arose in the context of planar n equals 4 super Yang-Mills. So first, let me tell you how the amplitude is really secretly a differential form. Now, normally we think about scattering amplitudes in supersymmetric theories as functions of some bosonic variables and some Grassmann variables that take care of all the helicity information in some on-shell superspace. When we talk about amplitudes in n equals 4 in terms of momentum twisted variables, there's 4 of them. There's 4 Grassmann parameters, and this has weight 4k for n to the k MHV amplitudes. So here's an example of some piece of an amplitude. It's something famous called an R invariant. It's a polynomial in the etas. Very good. Now, that's the usual picture. Now, all we're going to do is take those Grassmann variables eta, and we're going to replace them with dz. Okay? Dz's as differential forms are anti-commuting as well in exactly the same way. And so at the moment, this seems like just a totally dumb thing. I take eta and I replace it by dz, so that takes this function and it turns it into a 4k dimensional form. But it's interesting that it's a form just on the bosonic, the space of the bosonic kinematical data now. Now, what good is this? What good it is that if you take this function, now turn into a form, you can imagine doing things with it you couldn't before. You can integrate it on cycles. You can look to see if it has residues. In fact, only when you write it as a form can you recognize this object is really secretly a whole bunch of wedging of some d logs with each other. That's something that we've seen all over the place in the context of the Grassmannian and the positive Grassmannian, but here we're not seeing it with any auxiliary variables. We're seeing it directly on the space of the actual kinematical data. And so this move of talking about the scattering form allows us to expose the underlying positive geometry. It may not be obvious that this object is supersymmetric, but all of that stuff I don't have time to explain is kind of well known in the Grassmannian story, but now interpreted in the language of these forms. All right, so now, here in planar n equals 4, this is how this general picture that I told you works, and this is the new picture of the amplituhedron that we talked about with Hugh Thomas and Yara Trinka back in April. Very different than the original picture. Here, the kinematic space is just the space of bosonic momentum twister data. This essentially encodes the momenta of the particles. There's no helicities. So each one of them is a 4-dimensional vector. It's a 4 times n-dimensional space. We're looking for a 4 times k-dimensional form. K is less than n, so it's not top-dimensional. Now, what is this positive region P? Well, in the configuration space of just these 4-dimensional vectors, nothing else, there's a piece of that space that in the paper we refer to as having the correct binary code. Never mind what that means. When you actually look at the configuration of points, of vectors, there's a canonical way of projecting through points in the geometry down to a line, and when you get down to a line, the points that you have to have a fixed sign fluid pattern. Okay, but never mind. All you need to, for this purpose, all you need to know is that there is some property of what the momentum twister data looks like, which turns out to be equivalent, saying that all the physical poles are positive, and you have some maximal winding number. And I won't explain it, but this is really the entire description of what that space looks like, both at tree and at loop level. Right? So there's some piece, but there's some piece in the space of the bosonic momentum twister data, which is good, which is the positive space. Now, what is the subspace? The subspace is an affine translate of a given point in this configuration space. So I take a given point, and I imagine translating it in the direction of a general k-plane. So this is a linear subspace in the Grassmannian. If you think of the external data as the 4-plane in n dimensions, it's an affine translate of that subspace. It's a 4k-dimensional space. And interestingly, the data that specifies the space needs to satisfy a certain positivity condition. It needs to be in a certain positive Grassmannian. This is the only place where the notion of positivity a la the positive Grassmannian appears. Everything else, if you've never paid attention to any of the papers we've written over the last 5 years, you would not miss anything from that point on. Okay? There is no auxiliary space. Everything is defined purely on the bosonic momentum twister data. And the claim is that the intersection of this affine subspace with the binary code subspace is the amplituhedron. But it's the amplituhedron, now the image of the amplituhedron in the momentum twister space. All right, that's in momentum twister variables. What about in ordinary momentum variables? So we have ordinary spinor helicity, we have ordinary spinor helicity variables. And so there's something else that we can do, very natural. Imagine I gave you a list of all the helicity variables. Take a positive helicity gluon and negative helicity gluon. I want to combine them into one object, which has correct weights. So I just have to multiply by some d squared lambda and some d squared lambda tilde. I can do this even in a completely non-supersymmetric theory. I can do it in QCD and QED, so amplitudes are forms in all these theories. But if I do it for n equals 4 super Yang Mills, I get a parity. If I do this, I get a parity symmetric form of the on-shell. Starting from a parity symmetric form of the on-shell superspace, and I replace the etas with the d lambdas in exactly the same way, I end up with a 2n minus 4 form. Once again, that 2n minus 4 form is a bunch of d logs. And now you can ask, what's the analogous story there? And we have most of it, although not all of it. The tree amplituhedron avatar in momentum space is the following. If you take the external data with the correct binary code, and you ask what it looks like, just that data, we know how to translate it back into momentum, into lambda and lambda tilde data, then it turns out that the lambdas and the lambda tildes that you get, just as two-dimensional vectors, if you plot them, you'll find that the correct winding on this side means that there's a correlated winding between lambda and lambda tilde on this side. That lambda has to wind around k times and lambda tilde k plus 2 times, or the other way around. Okay, but once again, in this configuration space of lambda and lambda tilde, we know what the positive region looks like. It's this winding thing. We're still trying to figure out precisely what this subspace looks like, this 2n minus 4-dimensional subspace looks like, but it's some kind of analog of fixing the lambdas and lambda tildes to a kind of canonical celestial sphere. But once again, the intersection of those things should be the momentum space version of the amplituhedron. All right, so now for ages, especially as I was first starting to learn the subject, you learn that there's a baby version of the positive Grassmannian, which is the isosahedron. We already heard a little bit about the isosahedron a moment ago. And let me tell you what the isosahedron is purely as a combinatorial object, and everything you saw in the previous talk was essentially about its properties as a combinatorial object. So here's all it is. Imagine that you have graphs, a 4-point graph, and we're just going to imagine planar graphs, and we're going to look at all the possible factorization channels. So at 4 points, I can have this. I can have S and T channel factorizations. At 5 points, I can have factorization in 2 pieces. I can keep factorizing to 3 pieces. And so there's a chain of relationships here. Obviously, everything here can come from something there, but some of the double factorization channels only come from some of the single factorization channels upstairs and so on. Okay? And I'm not bothering to write down the one at 6 points, because it'll be extremely complicated. So at there's nothing magic going on. You just write down all these objects, and now what you'd like to do is think of this as actually coming from some interesting geometric object. That much is not obvious, but it's true. Okay? Oh, and I will also tend to draw the same thing. Instead of drawing the cubic graphs, I'll draw dual diagrams like this. Okay? So it's the same information. Now, it's quite beautiful that this network of inclusion relationships is that of a convex polytope in n-3 dimensions. And that's the isosahedron. Okay? That's not obvious. So here's what it looks like for n equals 4. Here are the 2 triangulations of the square that are now thought of as vertices. The whole square is the interior. Here's for n equals 5. Here are the complete triangulations, and here are the partial triangulations are the edges. Okay? And things are related in exactly the way you'd expect from the inclusion rule. This is the picture for n equals 6. You see, it's quite a bit more complicated and interesting. And it's not obvious a priori that there is a convex polytope, but there is a convex polytope associated with it. Now, the reason, so this should make it obvious why one wants kind of a baby version of all of this connection between geometry and amplitudes for the isosahedron. Because the isosahedron is a thing that combinatorially is just about factorization and nothing else. Right? So you would think that somehow the isosahedron has something to do with phi cube theory. And then these other things, amplituhedra and so on, are sort of fancier versions of the same thing, but you'd like to see it already at the bare simplest level. And I tried for many, many years, and there was no go. And the missing ingredient was the idea of the amplitude as a differential form, as I'll now explain, and that's going to let the whole thing now proceed. So let me back up and tell you a little bit about kinematics first, just Mandelstam kinematics. If we have n particles, then we can look at, then we have all the PA dot PBs. It's an n times n minus 3 over dimensional space. If I have an ordering for the particles, I can, as usual, draw the momenta as a polygon. I can talk about the distances between pairs of points that are really sums of consecutive momenta. And so, again, I can draw either a plain cubic diagram and write 1 over S12, S123, or I can draw the analogous dual diagram and just write the 1 over the x's. Now, here's an amusing little point, and I'll draw a Star of David since I'm in Israel, that the number of diagonals of a polygon is n, maybe that's wrong. The number of diagonals is n times n minus 3 over 2. Okay? Sorry. It was late at night when I thought of doing that. You should never do that. All right. Now, you see, this is exactly the same as that. So these xij's actually give us a basis for all the kinematic space. Okay? All right. Now, so what is the scattering form? Well, it's the most obvious thing. You go back and you take all the diagrams, but you multiply by a ds. Okay, so instead of this being 1 over s, you make a ds over s. This is dt over t. There's actually a sign that is important. I might say something about that later. But similarly, I could draw exactly the same thing in the dual language. But we're going to make an n minus 3 form now, just by summing over all triangulations or all planar graphs of just dx over x with a plus or minus sign over everything in the triangulation. That's going to give me an n minus 3 form. Not an amplitude, a form. Okay? Now I have to tell you something else. So this form is going to turn out to be, in exactly the story that I told you, this form is going to turn out to be the canonical form for an isosahedron. The isosahedron in momentum space, okay, in kinematic space. So there's been an isosahedron in kinematic space all along, and so here's how you find it. Exactly the way the general philosophy I was describing before. First, there's a positive region. In this case, it's just saying that all the poles of the cubic graphs or all these diagonals xij are positive. That's a giant simplex. Okay? But now I'm going to find a linear subspace in this big space, and the linear subspace is going to be picked out the following way. I'll ignore one edge, I take any two pair of non-adjacent edges, and I declare that their pi dot pj is a fixed constant. So that's giving me a linear subspace now. And it's important that fixed constant is negative. Okay, so if I put a minus sign here, this fixed constant is positive. So the intersection of this subspace with that positive region turns out to be a shape, an n-3 dimensional shape, which is the icosahedron. A very simple example at 4 points is I have s and t, which have to be positive, but this condition tells me that s plus t has got to be a positive constant, so I have to take this quadrant and intersect it with that line, which just gives me that interval, which rather trivially is indeed the n equals 4 icosahedron. Now, why? I think I don't have time to explain why this is true, but you can look at the slides, and better you can do it yourself. It has a two-line proof. Okay? And if you take that form as I defined it for you and pull it back to this subspace, you discover that all the wedges of the dx over x's, all of them, they're all proportional to the same thing, and what you're left with is just the sum of all the cubic graphs, which is just the amplitude. Now, the amplitude for what theory? Well, we know if I'm talking about planar amplitudes, it has to be amplitude for some amplitude for some bicolored theory. It needs to have another color, otherwise everything would vanish. Bicolor theory doesn't have just one partial amplitude, it has a whole bunch of partial amplitudes labeled by some set of permutations. Where's that information? That information is beautifully there in the facets of the icosahedron. In fact, one of the facets is associated with a particular partial ordering diagram. Any tree diagram like this can be colored with alternate black or white vertices, and if you take a walk through the graph, making a right turn at every black vertex and a left turn at every white vertex, as we got used to from the positive Grassmannian, that gives you a permutation. That permutation is the ordering. The pullback of the same form on a subspace that zooms into that facet is precisely the double partial amplitude. So, the bicolored phi cube theory fits into this general rubric. Now, exactly the same thing, except this isn't the curvy space, it's just a linear space, just all the xij is positive. This is another linear space. The intersection of these two linear spaces is the icosahedron, and the canonical form associated with that is just the amplitude for phi cube theory. What about gluons? We repeat exactly the same exercise. Now we look for a form which does not fix one ordering ahead of time. In fact, we demand that no matter which ordering you choose, there's an icosahedron associated with that, and that the form should have logarithmic singularities on that icosahedron. Okay? There's many things that we can do here, but if we have that this form also depends on polarization vectors and momenta, then it turns out, and this is a non-trivial result, that the only permutation invariant, on-shell gauge invariant, and minimal pole at infinity, means standard power counting, form that you can write down with these properties, it's unique. And the form is Yang-Mills amplitudes. Okay. Well, what am I talking about? Yang-Mills amplitudes have color. Where's color here? Color is kinematics. It's not color kinematic duality. Color is kinematics. This is a remarkable tiny point. Let's say I take one of these cubic graphs. I'm supposed to wedge together all the ds's here, okay? That's just the enumerator from the wedging. Now, it's a simple, beautiful fact that these objects made out of wedging ds's and things made out of exactly the same graphs dressing with color FABCs satisfy exactly the same algebraic relations, okay? And the reason for it goes back to something that we all learned in grade school, that if you have a 4-point process here with general momenta, PA plus PB squared plus PA plus PC squared plus PA plus PD squared is the sum of all the mass squareds on the outside, which is PA squared plus PB squared plus PC squared plus PD squared. And therefore, if I take the wedge of the sum of these things and wedge them into all the rest of them, I'll get 0. That means that this differential form associated with 3 graphs that are related to that way always add up to 0. So that's why the forms satisfy color identities. Therefore, you can take one of these objects and just replace those ds's by FABCs, and that gives you the Yang-Mills amplitude. All right, so I literally ran out of time, but if I can just have a few minutes, at least I want to tell you something about the worldsheet as a positive geometry, at least in the simplest first case. You can look at the slides for the rest of them. Okay, so I've now told you everything about a way of defining Yang-Mills amplitudes and phi-cubed amplitudes as canonical forms associated with an icosahedron that lives in just Mandelstam space. All right, now, of course, we've all seen, especially as string theorists, you've seen the icosahedron before. It's the most familiar object. It's just the moduli space of points on the boundary of a disk, mod SL2. So I described this as a bunch of two-dimensional vectors, mod GL1 for each one of them to get me to a boundary of a disk, and mod SL2 for everything. And you know that the boundary structure of this thing is precisely that of the cubic graphs, and so this is exactly the same. This moduli space is exactly the same as an icosahedron. Okay? In fact, in this language, we have a 2 by n matrix. We say all of its ordered minors are positive, and there's a n-3 form on the worldsheet that has the property that it has logarithmic singularities on all the facets of the worldsheet icosahedron. Okay, so there we go. There's a beautiful object out there associated with the icosahedron. It's a form with logarithmic singularities on the icosahedron. I want another form on another icosahedron in Mandelstam space with logarithmic singularities on it. Okay, well, what can I do? I told you in the very beginning that if you can find a push forward from one space to another, if you can find a mapping from this space into that one, so that the interior here goes into the interior there, then the push forward of the form here gives you the form there. So what is the equation that maps the worldsheet icosahedron into the Mandelstam icosahedron? You will not be surprised that there are the Kachazo-Yuan scattering equations. The scattering equations normally are thought of as equations. The S's are fixed, and you solve for the worldsheet variables, but you can also think about them the other way around. When you restrict to an n-3 dimensional subspace, as we're doing, then they're just linear equations for the S's. And remarkably, these equations you can solve for the S's, and as you scan over the worldsheet icosahedron, you just beautifully fill out the Mandelstam space icosahedron. Okay? So the scattering equations are the map between the worldsheet and momentum space icosahedron. Okay? And I think it's quite beautiful because this momentum space icosahedron is literally an image of the worldsheet. Absolutely, literally an image of the worldsheet in momentum space. Now, there's also some magic you can see backwards, as I told you before, that if you fix the sigmas, if you fix the S's, if and only if they're in one of these momentum space icosahedra, then the scattering equations have a single real solution for the sigmas inside the worldsheet icosahedra. All right, and of course, this push forward is precisely the CHY formula. All right. So there's a similar story for Yang-Mills theory. As I told you, the icosahedron turns out to be a baby version of the positive Grassmannian for G2n, the simplest positive Grassmannian for G2n. In fact, the icosahedron is what's called the tropicalization of the positive Grassmannian for G2n. And something we've gotten used to in the amplitude business is the second version of the worldsheet as positive geometry is actually positive G2n, thought of as the worldsheet of the twistor string. The push forward of exactly the same form, but now associated with the positive Grassmannian, on the support of the analog of the scattering, or the specialization of the scattering equations, which were known long ago as the RSV equations associated with the twistor string. The push forward there is exactly that form that I told you about for super Yang-Mills. And the final thing we have some strong evidence for, but we have absolutely no idea how to prove, is that the image of the twistor string positive Grassmannian worldsheet under the RSV push forward is the momentum space version of the amplituhedron that I told you about before. So everything has come full circle. All these things are connected. The strong evidence is that we find numerically the RSV equations have a single positive solution in the worldsheet positive G2n if and only if the lambdas and lambda tildes have exactly the strange winding number pattern that's precisely predicted by the amplituhedron. All right. So I will unfortunately not have time to talk about how any of this is related to perturbative string theory. I'll just say very quickly, if you have these canonical forms, we're pushing them forward. But why the heck not just integrate them on the worldsheet? That's the most obvious thing you do, just integrate them on the worldsheet. So why don't, inside the worldsheet icosahedron. So why don't we do that? We don't do that because the answer we get would be infinity. It has logarithmic singularities everywhere, so if we just straight out integrated it, it would be infinity. However, there's a very standard way of dealing with this that's done all over the place by mathematicians, for example, Gelfand and friends in the context of generalized hypergeometric functions, which is to weight the form by something that looks exactly like a Kobe-Nielsen factor. And you take literally the canonical form weighted by these Kobe-Nielsen factors. Now we can integrate them over the worldsheet isosahedron. And if we do exactly that, for example, for this Yang-Mills form, which on the worldsheet is completely fixed by the requirement of gauge invariance from the push-forward perspective, you take exactly the same form, you deform it with Kobe-Nielsen factors, and you integrate it. That precisely gives you the open superstring amplitudes. This is not a trivial rewriting of there's some work that needs to be done to establish, which has been done in the past, but to establish the connection between these two ways of thinking about things. All right. So now I've given you at least a taste of this set of ideas. We should think of amplitudes as canonical forms of positive geometries, and it allows quite a concrete relationship between many of these theories. And from my point of view, I think this picture is what these amplitudes really are. What I mean by that is that this is the sort of invariant property that uniquely fixes what the amplitudes are. Okay, that's what they are. They're forms with canonical kinds of singularities on these spaces. Everything we know, all the other things we know, of Feynman diagrams, recursion relations, push forwards from worldsheets, these are representations. These are ways of making pieces of these invariant facts obvious. But the object is sort of invariant and has this more abstract definition. And so I'll just end with both a little and a big question. A little question is, what's the worldsheet push forward for the original momentum twister amplituhedron? That's, ironically, after all this stuff, we actually don't know that. We don't know the analog of the worldsheet in momentum twister space. There's lots of circumstantial reasons to think that it's related to something that's still a quite mythical object that those of us have been pursuing for a long time, called the dual amplituhedron, but I don't have any time to explain what I mean by that. The big question is the following. So let's go back to the worldsheet. We see that if I push forward the canonical form on the worldsheet, well then, that's a representation of this thing that has this more abstract invariant meaning. Now, when I do a Kobe-Nielsen deformation, I get superstring amplitudes. It's hard for me to imagine that here the worldsheet isn't particularly fundamental. This is the more abstract invariant thing. This is the representation of it. It's hard for me to imagine that there isn't some analog of this object over here. In other words, I hope or I suspect that there is a more invariant question to which string amplitudes are the answer. The problem is that there's more. It's not just something simple like logarithmic singularities. We get more complicated functions. There's something interesting about their analytic branch cut structure. Something, I don't know. But by analogy to the existence of this picture for over here, of which this is just one representation, I somehow feel that the superstring amplitudes also, we'll come to see the worldsheet as just one way of representing something else, which is, I think, perhaps a very interesting question to figure out what string amplitudes really are. Thank you very much.
Nima, I just had a trivial question. When you're discussing the Mandelstam space, are you working in infinite dimensional momentum space?
I'm imagining that there's no dimensional constraints. Yeah.
But of course there are.
Of course there are, yes.
So what happens to the story when D is finite?
Yeah, I don't know. And that's something I think, in a sense, we have two extremes of this. So there's some, one extreme of this story is amplituhedra and the twistor string and all this stuff, which is D equals 4. And they're the kind of form that we're talking about is a more satisfying form because the sort of components are telling about the helicities, right? Then we have a different picture for the form in the Mandelstam space that somehow doesn't care about the dimensionality at all. What we don't have yet is, I think, a sort of a clear picture for a deep relationship between those two. But I think if you have a fixed D, somehow it makes more sense to talk about the kind of form that we talked about in D equals 4. And I want to stress that what I talked about, you can do for the standard model. This idea of turning scattering amplitudes into differential forms is a generally interesting one because after you do it, you can find geometric structures in it that are hard to see beforehand because you can ask questions about residues and integrating on cycles and so on. So I suspect in finite D, that's what we should do. There's a lot of sort of formal similarities between the structure of the scattering equations and the link between the Grassmannian and the external data space. But somehow there's something a little bit less natural seeming to me anyway about working directly in the Mandelstam space. So I agree with you. What's certainly true though is that at least on the worldsheet side, exactly the same complex of equation. You start with the worldsheet, you're solving the scattering equations. Something special happens in 4 dimensions where you can introduce spinor helicity variables. The equations turn into the RSV equations. But you do exactly the same thing to it. You push it forward. And in one case, you push it forward, you get this Mandelstam space form that I talked about. In the other space, you push it forward, you get this different kind of form. So they are linked somehow.
All right. Thank you. As we are late, let's have a coffee break. Thank you.